Basically, what I'm doing is a Zoom meeting with no one in it. And then you can record the Zoom meeting and it's saved out and converted, and I have to upload it and all that junk. But it's basically software I'm using is Zoom. All right. Today's dry lab is on significant figures. Now, in science disciplines, things like geology, engineering, chemistry, physics, biology, usually we gather data by using some kind of an instrument. And all instruments, without any exceptions, have an error of some kind. The more money you pay, the smaller the error. The less money you pay, the bigger the error. For example, I cook a lot at home. And my digital scale at home cost $18. The digital scale you use in the lab costs $1,000. Which do you think is more accurate? One's in the lab. The lab goes to 3 decimal places. Mine goes to 1. And it's iffy at that. So what significant figure has to do with is how precise that number is you get out of the instrument. So we're looking at 2 things. One is, how do you know how many significant figures are in a number? And then what are the rules that you use to manipulate them, like in math, addition, subtraction, multiplication, and division. So that's what the dry lab is all about. There are 6 pages of practice. All right. Let's go down here and look at some numbers. The first number up there, 1, 2, 3. I always ask people to kind of guess on these. How many sig figs do you think that is? This is the hardest one. 3. 3 sig figs, okay? You look at the next one, 1.23. That also has 3 significant figures. Now I abbreviate significant figures as sig figs or SF. Writing out longhand significant figures is a pain. So SF. 0.23. 2 significant figures, not 3. The 0 in the beginning does not count. 1.01. 3 sig figs. So the 0 in the middle always counts. Now this is a tricky one. 5.0. Most people say 2 sig figs, but it's really 1 significant figure, because zeros at the end sometimes count and sometimes don't. Now the trick is decimal point. Notice the one below it, 5.0 decimal point. It has 2 sig figs because there's a decimal point present. Whenever there's a decimal point, regardless of where it is, zeros at the end count. So we got 3 situations with zeros. In the beginning, they never count. In the middle, they always count. And they count in the end if there's a decimal point present. Now going back up to 5.0, no decimal point, math departments will say it's ambiguous. So on your worksheet, as an example, they'll say ambiguous. Cross off ambiguous. 99% of chemistry departments don't count that as ambiguous. They count it as 1 sig fig. Okay? So if it's zeros at the end, doesn't matter how many zeros. If there's no decimal point, they don't count. Yeah. Which one? One that's circled? Okay, so 254, what people were guessing. I asked people, and they'd come up with 2 and 5 and 4. Okay, first of all, does it have any zeros there? Yes. Where are they located?
Beginning and after the decimal.
But they're in the beginning. Okay. What's important is they're in the beginning. That means don't count. Now, if those are at the end and decimal point, then they would count. So in the beginning, period, no exceptions. In the middle, always count, no exceptions. On the end is when you have to say, is there a decimal point there?
Okay. That would be 2.
2, yeah. All right, you had a question too, didn't you? Yeah. 2. Because if 0 is at the end, that means you have to look for a decimal point, and it's there, so it counts. And the one above it doesn't have the decimal point, so it doesn't count.
The one that chooses all your level.
The one below it.
So the point 0, the 0, 0, these are just 2 numbers. They don't,
The 2 numbers count,
the 2 last one, 2 zeros before it.
correct, because it's in the beginning. Beginning ones don't count. What was the example? Well, the zeros would be in the middle, and in the beginning, we wouldn't count. That makes sense? If there was one in the beginning. Yeah, like you had, so if we had, that would be 5. Okay. Count because they're in the middle. Yeah. The one in the beginning doesn't count because it's at the beginning. Yes. That's right. Okay. Scientific notation. We're going to talk about scientific notation there. Yeah. Nope. You got to put it there if it's there. Yes. If there's a decimal point after the 0, the 0 then counts because it's at the end with a decimal point. No decimal point. And when you do math, you do a math problem, and all of a sudden your answer has to be 2 sig figs for some rules, and your answer is 50. To make it 2 sig figs, decimal point there. Now it's 2 sig figs. Yeah. Say again. It's to force it to be 2 sig figs. Because whenever you measure anything, the last digit is plus or minus 1 or 2. So with 50 with no decimal point, that means that 0 is plus or minus 1. So it could be 49, 50, or 51. By putting a decimal point there, it's much tighter, much more precise. It's just the more sig figs, the more precise it is. So if we're forcing more sig figs by putting a decimal point at the end, we're making it more precise. I know. Yeah, I understand. You probably haven't seen this before till tonight, right? Or today? Yeah. Okay. Scientific notation. Now, scientific notation, I'm going to go over a little later, but it's got two parts. Scientific notation has got two parts. It's got a number from 1, actually 1 to 10, but not 10. And then an exponented number as well. They always have two parts, no exceptions. Every number you can put in scientific notation. For example, the number 5. What is 5 in scientific notation?
Bucket first.
No, that would be 50.
If you're multiplying by e, but just 5 to the first power by itself. Like
But scientific notation, remember, has two parts. Where's the 10?
multiplying by
Not 10. Every number can be scientific. Yeah. Well, that would be 0.5. You guys are jumping around the only number left. You said -1, he said 1. 0. That's right. So any number to the 0 power is 1. It's called the identity postulate in math. Can be 1,000,000 to the 0 power is equal to 1. Okay. Now, the purpose of scientific notation is to make awkward numbers less awkward. So when you say which is more awkward, the one on the right or the one on the left? The one on the right. So some teachers make you put everything in scientific notation. I think that's personally BS. Because the sole purpose of scientific notation is we're going to be working with some very, very large numbers in here. Some very, very small numbers. Very, very awkward. Some of them have like 23 zeros after the number. That's a really awkward number to put in your calculator. So we do it in scientific notation, which makes it significantly less awkward. So 5 to me is a heck of a lot cleaner than 5 times 10 to the 0. So don't put it in scientific notation. Think of 1,000. Anything over 1,000, put in scientific notation. Anything under 1,000, put in scientific notation. Everything in the middle, just leave alone. Now, you can always put it in scientific notation in my class if you'd like to. I won't mark it wrong at all. I'm just saying, though, that the spirit of scientific notation is to keep it simpler, less awkward. Okay, so in the spirit of that, and it's one person may say this number is awkward, so the person say it's fine. It's fine, either one, as long as numerically they're the same, no problem. Okay, so going back to scientific notation, 1.2 times 10 squared. And that's the same as 123. Now, for right now, we're talking about significant figures. So to do significant figures, you look at the first number, not the exponential number. So how many sig figs is 1.23? 3. So that number has 3 sig figs. What would this guy here have? They don't count. This counts because there's a decimal point. It's 3. Now in lab today and lab tomorrow, you're going to practice this out the yin yang. I mean, a lot. Oh, by the way I grade dry labs is I randomly choose 10 problems. And that way I can get them graded in a timely manner. Usually I take a couple of problems from each section. So if you already know how to do this lab, you can do this worksheet at home if you like. But I'm going to be there to help you with the problems. But if you already know this stuff, you can do it at home. But just don't not do it. Because I need to look at those 10 problems. Okay. So are there any questions about determining sig figs? Okay, there's the zero rules up there. Middle zero always counts. Beginning zeros never count. And the zeros in the end count if there's a decimal point. Okay, so there's two situations where we're using significant figures. In here, 99% of the time, we're going to be using them in multiplication and division. So most of the time, the multiplication, division, and exponentiation rules will take precedent. All right. Okay, when we're multiplying, and the multiplicative inverse of multiplying is division, and exponentiation is a shorthand way of multiplying or dividing. So they're all basically the same operation. Whenever we do anything with a multiplication, division, or exponentiation, you look at the significant figures in each of the operands. And your answer is going to be the least. Now, let me give you a metaphor. We have a chain. Chains are made up of links. Okay, and I need to go through and look at the strength of each link. Each link can hold 100 pounds, except one of them can hold 10 pounds. So I make a chain out of all these links. How much can I lift with that new chain now I made? 10 pounds. Because when we go over 10 pounds, the weakest link breaks. Doesn't matter how strong those other links are. Same with significant figures. The answer reflects the least precise number. Least precise number is the least amount of significant figures. Okay, so let's look at some examples here. All right, let's look at first thing you want to do is look at what kind of operation are we doing? Okay, we're doing multiplication. That means we need to look at the significance of both those numbers. How many sig figs is in 1.25? 3. We're about 2.50. So what is our answer sig fig wise going to be? 3. Doesn't matter if your calculator goes out 29 places. It doesn't matter. Our answer is going to be 3 significant figures. Now my calculator says but that's how many sig figs? Yeah. Okay, so how many sig figs is this? 4. Okay. We need to be 3. So this is how you convert a number from one sig fig to another. Okay, our answer should be in 3, so we go to the 4th place. It doesn't matter what's past that. 4th place is the only one that counts. At 5 counts. If it's 5 or more, it goes up by 1. If it's 4 or less, you drop it. So our final answer is going to be, and I will usually do this. I'll say, that's just for your clarification. That this should be 3 sig figs. Yeah.
So. For the 2.5,
The 0 at the end counts because there's a decimal place. Correct. Correct. Okay, so okay. Fractions, as you know, are division problems. So we have 1.25. So our answer is going to have 2 sig figs. This is what my calculator gives me. How many sig figs is that? 1. No, está bien. How can we make it 2? Add a 0 in the end. Exactly. Now it's 2 sig figs. So you force it up or down. Another way to do it in scientific notation. 5.0, we ignore this. 5.0 is 2 sig figs. And in my calculator, it was 5 times 10 to the minus 1. So we had a 0.0 there to kick up the sig figs to 2. Now, it doesn't matter how many operons you have. You could have 12 operons, and you have to analyze all 12 to see which one is least. Now, on your first test, you're going to have a take-home problem. Unit 1 has got a lot of conversion factors, got significant figures. It's something called dimensional analysis. And your take-home problem is going to be really long and involved. Not hard, just long. That's why it's a take-home problem. And there's going to be many, many steps. And you're going to analyze all the steps for sig figs. And then that'll determine your final answer. Okay. And the inverse of addition is subtraction. So the rules that apply for addition also work for subtraction. Okay. Much easier. Your answer is going to have the least number of decimal places. Okay, 1.005, 3 decimal places. 0.1, one decimal place. Our answer is going to have how many? One decimal place. So we go to here. From 0 to 4, we drop it. So our answer is 1.1. Same with subtraction. Now, in this class, we're going to be using the periodic table a lot. And there's a decimal number in each of those squares. And the decimal number is 2 decimal places. That's called a molar mass. So I've already rounded everything to 2 decimal places. When you get to 1A, depending on your teacher, sometimes they go eight places and sometimes 7, sometimes 2. In this class, we're using this one. So everything is already rounded for you. So when we start using that in unit 4, you're going to be adding up all these decimal numbers, but they're already rounded for you. So they're really easy to use. But whenever we're in an addition subtraction problem, you look at the number of decimal places. So they're pretty easy. Okay. Okay. So we have a combination of multiplication and division. So if we put this in a calculator, crank it out. That's what my trusty calculator gives me. All right, so this is a combination of multiplication division. So we have to analyze each operon, the number of sig figs in it, and that'll determine our sig figs and our final answer, which you can see calculator. Most calculators do 29 significant figures underneath the covers. And then the display, depending on your calculator, will round to whatever you tell the display to do. Okay, so 1.56 is how many? Zero 0.12, 1.23, 6.581. So our answer is going to have 2 sig figs. That means we go to the third significant figure. Notice the zeros don't count because they aren't significant figures. Okay, and that's 9, means that 4 goes to a 5. So our answer is add. Okay, like addition. Zero 0.01. Okay. But I mean, this is the entire 035. What would our answer be? Is that the correct answer? 0.1. Now that's, I don't know about you guys, but intuitively, you're going, what? Right?
So you can do all these like multiplication division, and then if you just add a 0.1 or whatever, it will go to the first.
That 0.1 is a really unprecise number. So it's really precise number and garbage. Garbage in, garbage out. So does that make sense? Why it's 0.1? Yeah, I know, it's goofy. But again, you're not going to have very many problems like this stuff. So intuitively, to me, when I first saw this way back in when did I take high school math? 1966, when I took high school chemistry. I saw this and went, what? It took me a long time to get comfortable with this. That's a really good question, though. Remember I told you I was old? I went to Foothill High School. The first year it opened, my class was class of 68. Okay, this is just a matter of practicing it. Hmm? This is just a matter of practice. And that's what we're going to do in lab. So what we're going to do is we are going to start lab early today. Since this was the introduction I was going to give you for this anyway. So this is, let me take you over to the lab for all the Friday people. And I need to come back here and take down all this equipment. Okay? Are there any questions about what we've done so far? You'll get an opportunity in lab to ask away. This is what's really nice about dry lab. I have a lot of time with you.